Hi all, so today we are going to be looking at chapters 4 through 6, and on Blackboard you can find the entire PowerPoint for those chapters, along with annotated notes that go through the entire PowerPoint. But for the purpose of this video, we are going to focus on a condensed PowerPoint that mostly focuses on the main ideas and the examples, so that we can see how to apply these problems in Excel. So we're actually going to be talking about 3 distributions. We'll be talking about the binomial distribution, the Poisson distribution, and the normal distribution today. So what you can see here is the binomial distribution. So we are given a binomial formula that would allow us to do these by hand or with a calculator or something like that. You can see that the binomial formula equals this right here means combination. So a combination of n over x times p to the x times q to the n minus x. And then you see in purple here, I have the mean and the standard deviation for calculating for a binomial formula. It's important to understand what the binomial distribution is covering. So in a binomial distribution, you only have 2 possibilities. It's either a success or a failure. So if it's a success, we use it as x. X is our number of successes. And then P is the probability of a success, and Q is the probability of a failure. Yes. So in this problem here, it says, suppose you play a game that you can only either win or lose. The probability that you win any game is 55%. So that's our probability of winning, which in this case would be a success. So we would use 0.55 for, and the probability that you lose is 45%. So that is, loss would be a failure. Each game you play is independent. If you play the game 20 times, so 20 times is the number of times we play the game, so the number of trials, write the function that describes the probability that you win 15 of the 20 times. So we want to talk about if we had 15 successes. So yes, we could put this into a formula, right? We could put it into that binomial formula we just saw, and it would look like this. The probability that x is equal to 15 equal to the combination of 20, 15 to 0.55 to the power of 15, because that's the probability of success to the number of successes, and then 0.45 to the power of 5, because that's the probability of failures to the number of failures. And then we could calculate this. We can calculate it by hand, or we can calculate it with a calculation device like a calculator. But we mostly use Excel in this class, so let's take a look of how we would do it with Excel. So we are going to take a look here at this Excel file, and we're working on example 4.2. You do have this Excel file up in Blackboard for you. You're going to see that it has 2 tabs. This first tab is just got the example problems we're going to go through listed, so that you can work along with me. And then the completed Excel gives you the actual commands that we are going to be doing on these problems. So you can go back and refer to those after the class if you need a reminder. So for this one, because we're doing a binomial distribution, we're going to start with equals, and we're going to start typing binom. You see we have binomial.dist. That's what we're going to use here. It wants the number of successes, which was 15, the number of trials, which was 20, the probability of a success, which was 0.55, and This cumulative, we're going to put that it's not cumulative. We're going to put false because cumulative means that we want all the values from 0 up to 15 added together. We don't want cumulative here. We're just being asked for the 15. So you see here we get 0.0365. So with that being the case, here our probability is 0.0365. So we are going to be using Excel for this. So let's continue on. So approximately 70% of statistics students do their homework in time for it to be collected and graded. Each student does homework independently. In a statistics class, 50 students, what is the probability that at least 40 will do their homework on time? Students are selected randomly. Okay, so this is a binomial probability because you can either succeed or fail, right? So here in this first question, it says this is binomial because there's only a success or a failure. You only do your homework, which is a success, or you don't do your homework, which is a failure. The probability of the success is the 70 because 70% of students usually do their homework. So if we are interested in the number of students who do their homework on time, then how do we define X? So X in this case would be the number of students who do their homework on time. It's that simple. So the number of students who do their homework on time is our X, that part of it. So what value does X take on here? So what is the probability at least 40 will do their homework? So X in this case is going to be 40. It could be any value from 0 up to 50, right? Because we're talking about a class of 50. Failure in this would be somebody who didn't do their homework on time. And then our Q in this case would be 0.3 because if you do 100% minus 70%, you get 30%. So 3.3 is our probability here. So the word at least translates to an inequality, and the inequality we're looking at for this problem here when we're talking about at least would be greater than or equal to, because we want at least or equal to get it. So in that case, our problem changes a little bit. So let's go look, if we were to solve this, how it would change what we put into Excel. So here, I'm going to start with an equals, but I'm going to keep in mind that we're doing greater than or equal to. When we do these problems, it always gives us less than in Excel. So to compensate for that, we can do 1 minus to get something that's greater than. And we're going to do binomial distribution again. And the number of successes, well, we want it to be greater than or equal to. So theory-wise, if we're doing greater than or equal to, and the binomial distribution can only give us strictly less than, we're going to take our X and subtract 1. So we're going to use 39 here instead. So our number of trials is 50, and the probability of a success is 0.7. And this time we are accumulating it. We're adding everything together. So we're going to use true in this case. And so we get 0.0789 as our probability here. So I know that we did the problem differently, and the reason we did the problem differently is because of 2 things. We didn't have the equal sign, and we weren't using strictly less than. So to help us understand this, we're going to look at a table in just a second that helps us know, based off of the verbiage, how we should be calculating our formulas. So this is a kind of like a vocabulary review sheet to let us know, based off of the words that are being used in the problem, how we would do the command in Excel. So this is going to be very helpful for you. I would encourage you to learn this. Use it on your test. This is really important because it helps you go from English language to what that means mathematically. You'll see here that I have a note that you do the same thing with Poisson distribution, and it follows the same rule, except for Poisson distribution, you just use your x and your mean. And so when you're doing these problems, like for this first one, it's Poisson dot distribution, x minus 1, then the mean, then true, and so on. So I will allow you to refer back and forth to this as you are working. So the next type of distribution we're going to look at here is the Poisson distribution. The Poisson distribution is a lot like the binomial distribution, but it's looking at things over time instead of looking at things during a particular time period. I'm sorry, instead of just looking at like this one time, we're looking at x equals 15. We're looking at things over time here. So this you can read for yourself. It goes over the Poisson distribution. I just want to point out that the mean we're using here is our lambda. So our lambda is our mean, and we use lambda in our formula. So that's important to realize. We use our mean in our formula. And then our standard deviation is also our lambda. So no, this is our variance. Our variance is lambda. So our standard deviation would be the square root of lambda. Okay, there we go. So let's continue and look at an example of this type. So a bank expects to receive 6 bad checks per day on average. What is the probability of the bank getting fewer than 5 bad checks on any given day? Of interest in the number of checks the bank receives in one day. So the time interval of interest is 1 day. Let x equal the number of bad checks the bank receives in 1 day. If the bank expects to receive 6 bad checks per day, then the average is 6 checks per day. Write a mathematical statement for the probability question. So if we're looking at this, we're being asked for the probability that x is less than 5. And we're told that lambda is equal to 6 here because in 1 day we would expect to get 6 bad checks. So if we wanted to do this with the Poisson distribution, we can go through the logic behind this problem. We can see that it's strictly less than, and so we can take a look and we can put it into our calculator or Excel. So let's do that. So for this one, before we do that, let's just refer back to the sheet. So you know how to use the sheet, right? So we're doing x is less than 5 here. So if we take a look at the sheet, the strictly less than right here tells us that we're doing x minus 1. So we're still going to execute that x minus 1 on the Poisson distribution. So when we do it in Excel, we're going to do equals, and we start typing Poisson for Poisson distribution. And our x is going to be 1 less. Well, we can just do our x that we normally have, which is 6, or the x that we want here. Our x in this case was 5. We're going to do 5 minus 1 right here to indicate that it's x minus 1. You can put that inside of the problem so it looks exactly like what you're doing on that sheet, what that sheet tells you to do. And then we can put the mean, and then this is true because again we want less than, so we are talking about things that are accumulated. So in this case we get 0.2851 as our probability. So here, the probability that x is less than 5, when we put it in Excel, gives us 0.2851. Like I said, you can refer to the annotated notes, and they're more descriptive than what I'm writing here on your screen here. The purpose of this video is mostly to show you how to use Excel and go over the highlighted points. All right, so example 4.13, you notice that a new reporter says on average 2 times per broadcast. What is the probability the new reporter says more than 2 times per broadcast? This is a Poisson problem because you are interested in knowing the number of times the new reporter says during a broadcast, so during a time period. So when it says what is the interval of interest here, we're talking about one broadcast, right? That is our time period that we're looking at. So one broadcast. When it says, what is the average number of times the news reporter says during one broadcast, that's 2. So X can be values anywhere from 0, she could not say at all, 1, 2, 3, and pretty much so on. The probability question that's being posed here is the probability that it is greater than 2. So that X is greater than 2. So we could go back to that sheet and see what the rule is for greater than. So if we're looking at greater than, we would do 1 minus. We're doing Poisson distribution in this case. So I'm just going to put p.dist to indicate that Poisson distribution. And then we're using our x exactly as it is and our lambda. So if we go execute that in Excel, we're doing 1 minus. We're putting in Poisson distribution. The x this time is not going to change, so it's just going to be 2. Our mean is also 2, and we are doing cumulative. So we're going to say true and click enter. So the probability that she will say more than twice would be 0.3233. So when we go back to this problem here, this probability is equal to 0.3233. So it's also important to be able to look at these distributions in table form and kind of get an idea of how you're going to do this. So Leah answering machine receives about 6 telephone calls between 8 a.m. to 10 a.m. What is the probability Leah receives more than 1 call in the next 15 minutes? So if we let X be the number of calls Leah receives in 15 minutes, the interval of interest is 15 minutes. If Leah receives on the average 6 telephone calls in 2 hours, and there are 8 15-minute intervals in 2 hours, then Leah receives 6 out of 8, or 0.75 calls in 15 minutes on average. So this one shows you that if you are changing from, if you're given a mean on a particular time period and then you're asked for a different time period, so we were given hours, now we're being asked for minutes, we have to find that lambda ourselves. So that's important to realize when you're working on these problems. Sometimes you need to find the lambda. It's not just given to you. And so this one shows what that would look like in this case. So let's go ahead and take a look at some examples. So, according to a survey, a university professor gets on average 7 emails per day. Let X be the number of emails a professor receives per day. The discrete random variable X takes on the value X equals 0, 1, 2, so on. The random variable X has a Poisson distribution of P7. The mean is 7 emails. What is the probability that an email user receives exactly 2 emails per day? So this one, we don't have to change our mean. Our mean's already given to us. So for A, we're going to do exactly 2 emails. Probability receives at most 2 emails. And what is the standard deviation? So we're being asked several different questions here. So the first one that we're being asked is exactly 2. So we want the probability that X is equal to 2. The second says at most 2, so we want the probability that X is less than or equal to 2 if it says at most. And then the standard deviation, we know that our standard deviation squared here, or as we would call it, our variance, is lambda. So if we want our standard deviation, we would have to take the square root of both sides. So we would do the square root of lambda here to give us our standard deviation. So in this case, that's the square root of 7. You could use a calculator to calculate that. You could use Excel to calculate that. But you would get approximately 6.6 regardless if you used, 2.6. Regardless if you used a calculator. But we are going to look at how to do all 3 of these in Excel. So for the first one, we're doing exactly 2. So we're doing Poisson distribution, where we have 2. Our mean is also 2. And we are using false here because it said exactly 2, so it's not cumulative. Okay. Oh, and our mean's not 2, it's 7, right? 7 is the average number of emails per day. So our probability there is 0.0223. So then if we look at one where we are doing it as B said, which it was at most, that would be equal to Poisson distribution. Our X this time is 2 still because it's at most. And then 7. And this time it's true because we want to add all of them. So we get 0.0296. So there is a difference between less than or equal to and less than, right? So we want to make sure that we're understanding the difference between cumulative and not cumulative. Cumulative is when you have any inequality. Not cumulative, or when you put false on cumulative, is when you have an equal sign. So that's important to realize. And then, of course, that last one we already kind of looked at, but it would just be the square root. So you can type SQRT for square root and put in your lambda, which was 7, and we get 2.6458 as a more exact answer. All right. So here it says, text message users receive or send an average of 41.5 texts per day. How many text messages does the text messenger use or receive or send per hour? So what you need to realize here is we're doing a difference between per day and per hour. So in this one, we're actually trying to figure out that lambda because we're being asked for things on a pure hour and we're given a day. So if in one day we have 41.5 text in one day, well, we know that we have 24 hours in a day, right? So we want to know, we know that there are 24 hours in a day. And what we're trying to figure out here is how many texts there are per hour. So if we're looking at that, we see how we have text over hour as what we're trying to get. So we can take this text and divide by this hours, and these are essentially going to cancel, and we should get our answer. So we're just going to do 41.5 divided by 24 hours, and when we do that, we're going to get 1.7292. So the lambda we're going to use in this case is going to be 1.7292. So the next part, B, says what's the probability that text message users receive or send 2 messages per hour? And then what is the probability that a text messenger receives or sends more than 2 messages per hour? So we're asked for 2 messages per hour, and we're asked for more than 2 messages per hour. So in this case, for B, hold on, what did I do to my system?